Welcome to Lesson 17, Imaginary Numbers. You say, what are imaginary numbers? I mean, there are numbers that don't exist. There are numbers that one can only imagine. Well, that's just a name given in mathematics to the numbers that are created to explain the square root of a negative number. And we've seen the square roots of negatives. You recall back we talked about the solution to quadratic equations, and we had the discriminant, and if the discriminant was negative, we said there were no real answers. And since the opposite of real is imaginary, that's where the name imaginary comes from. Let's go back. Let's go back, look at the first visual, go back to the solution of a quadratic where we said there was no real answer. We have x squared minus 2x plus 5 equals 0. And you'll recall that b squared minus 4ac was the discriminant. And in this case, it's equal to negative 16. And therefore, we could say, we didn't say this. At this point in time, we said, hey, there's no real solutions, no real roots. But we could say that x equals 2 plus or minus the square root of negative 16 all over 2. Now, what this number means, we're still not sure. And in fact, back hundreds of years ago, before the invention or creation of imaginary numbers, this is how they wrote the answer. And if someone said to you, well, what does it mean back then? You'd say, I don't know, but that's the answer. And then some time ago in the past, we created imaginary numbers. And let's go to the easel and take a look at what these things are. I mean, basically, what somebody said is, hey, let's start out with the square root of negative 1. And let's give it a name. Now, they could have called it Fred. They could have called it Mary. But instead, they called it I. The letter I for imaginary number. And you can say, well, so what? Well, why do they do this? And a lot of mathematics is created, you see, not because people have a reason to apply the mathematics, but because they would just like to play around with it, see what happens, what if we do this kind of thing. And then many years later, someone else comes along and takes that mathematics and uses it. It happened here. Initially, I was just a symbol used for the square root of negative 1. And later on, when the generation of three-phase alternating current electricity came about, the square root of negative 1 was used by electrical engineers. And if you want to know more about that, I suggest you go to an engineering college and major in electrical engineering. But many years since I took that course in electrical engineering, so I don't want to tell you something that's not true. But they do use the notion of the square root of negative 1 in electrical engineering. Now, what do we do with this? Well, what we could do with this is say, okay, what does this mean? What if we take I squared? Now, remember, when you square something, in the past, you always got 0 or a positive. That's because you were squaring a real number. What if you squared an imaginary number? Well, when you square a number, you multiply a number by itself. And therefore, when I multiply I times I, based on this definition, I must get negative 1. So now we can write, this is basically two ways of writing the same thing. If the square root of negative 1 is I, then I squared is negative 1. How about the square root of negative 4? Well, there's a couple of ways of looking at that. The first thing we can do is factor out the 4, and the square root of 4 is 2. And what's left inside is the square root of negative 1. The square root of negative 1 is I, so we can say 2i. And of course, that would mean that 2i squared would be negative 4. In fact, let me write that up here, 2i squared, because I better put that 2i in parentheses, just to make sure I know I'm squaring 2i. And of course, 2 times 2 is 4, and I times I is negative 1. So again, these two statements are the same thing. And therefore, any square number, 9, 16, 25, if we put a negative in front of it, we could say the square root of negative 25 is 5i. And how we use this, we could see in the next visual. We go back to our problem where our answer was 2 plus or minus the square root of negative 16 all over 2. And what do we see? We see that the square root of negative 16 is 4i. And therefore, we can write our answer as shown in the highlighted line 3 as 2 plus or minus 4i all over 2. Since both 2 and 4i can be divided by 2, our final answer is 1 plus or minus 2i. Now what we have here is something called a complex number. A complex number is made up of a real number, a, and an imaginary number, bi, where b is a real number. We look at the next visual, we can see some examples of this. For example, 2 minus 3i is a complex number. The 2 is the real part. The negative 3i is the imaginary part. And together they make a complex number. Okay? Another example, just to show you that we can have fractions and even square roots in our complex number, is to the right of it. Negative square root of 7 plus 2/3 I. The negative square root of 7 is the real part, because if you square the negative square root of 7, you get 7. You get a positive number. The imaginary part, of course, is plus 2/3 I. You square that, and you get negative 4/9. The negative coming from the I squared, the 4/9 from the 2/3 squared. So we have an imaginary part, the 2/3 I, and a real part, the negative square root of 7. Together they make a complex number. A real number, like 5, as indicated on the third line, can be written in complex form, that is, as 5 plus 0i, since 0 times I is nothing. An imaginary number, such as 2i, can be written also as a complex number, and that's seen on the bottom line of in this visual, which is 2i is 0 plus 2i. Now, what can we do with these complex numbers? Well, quite frankly, we can do everything with those numbers that we can do with any other kind of number. We can add them, subtract them, multiply, divide them. And of course, they're very useful because we saw they can be solutions to equations. So let's first of all go to the board and take a look at some addition and subtraction problems. And here's an example of the addition of two complex numbers. 3 plus 5i plus 9 minus 7i. And you say, how come you have those numbers in parentheses? I really don't need to have them in parentheses, but I want to really indicate that this is one complex number added to a second complex number. Well, in addition, we always add things that are the same. When we're adding polynomials, we can add x squareds and x squareds, x's to x's, constant numbers to constant numbers, and we can never add x's with x squareds. Same thing here. When we add two or more complex numbers, we add the real part with the real part. 3 plus 9 is 12. And we add the imaginary part to the imaginary part. A positive 5i, negative 7i, is negative 2i. Okay. So there's an example of adding two complex numbers. Let's take an example, and the board here, of subtracting two complex numbers. You may say, for complex numbers, this is not too difficult, and it really isn't. The name complex doesn't mean they're difficult, it just means it's made up of the real and the imaginary parts. So let's take a look here at negative 3 plus 8i, in parentheses, minus 7 minus 10i. Now, depending how you learn to do this, you could change all the signs in the second number and add, or we could just subtract. The negative 3 minus 7, you'll recall, is negative 10. And a 8i minus a negative 10i is the same as 8i plus 10i, so that's plus 18i. And again, at this point in time, we're simply manipulating symbols. I mean, what does this mean? I don't know. It just simply means if I have this number and I subtract this number, I get the answer. Okay? It's not something we can do on our fingers, quite frankly. Now, how about multiplication? Let's take a look at the next visual, which gives us an example of multiplying two imaginary numbers first. This is 2i times negative 3i. And we multiply the sign, a positive times a negative would be negative. We multiply the numbers, 2 times 3 is 6, and I times I is I squared. So we get, as shown in line 2, negative 6i squared. We're not done yet. Because unlike a variable like x or y or a or b, I has a meaning, and I squared is negative 1. And thus, negative 6i squared is negative 6 times negative 1, or a positive 6. Notice, all these years you've been saying well, a negative times a positive is a negative. When you're dealing with imaginary numbers, a negative times a positive is a positive. All the rules are reversed. You don't have to worry about remembering that. Just remember that I times I is negative 1. Let's look at the next visual, which shows us the multiplication of two complex numbers. You can say, you know, if those i's were x's, it would look like that FOIL method, multiplying two binomials. And you're absolutely right. The only difference is that when we multiply the I term times an I term, we don't get an I squared term. We actually do, but we change the I squared to negative 1. And on the second line of that visual, which is highlighted, we can see that 2 times 4 is 8. 2 times negative I is negative 2I. Positive 3I times 4 is a positive 12I. And a positive 3I times a negative I is negative 3I squared. Now, the only thing we've done on the next line is to change the negative 3i squared to a positive 3, remembering I squared being negative 1. We combine like terms. We can combine the real terms, 8 and 3, to get 11, and the negative 2i and the positive 12i are combined to get a positive 10i. Thus, the answer, 11 plus 10i. The next multiplication we're going to do is going to lead us into a very special circumstance. So let's look at the next visual. What is special about the two complex numbers at the top of this visual? If you look carefully, you'll say they look the same, except the first one has a plus sign in between the real and the imaginary terms, and the second parentheses has a minus sign. And you're right. And look what happens. The second line, which is highlighted, shows us that 3 times 3 is 9. 3 times negative 5i is negative 15i. Positive 5i times 3 is positive 15i. And 5i times negative 5i is positive 25. We've kind of skipped a step. It really is negative 25i squared, but negative 25i squared is a positive 25. Combining the terms, we get our answer. Wait a second, we combine negative 15i and a positive 15i, they drop out. They cancel. And we're left with 9 plus 25, which is 34. So we've multiplied two complex numbers, and we've gotten a real number. We've lost the imaginary part. And this is called a conjugate. That is 3 plus 5i and 3 minus 5i are conjugates. Specifically, a conjugate is shown on the next visual. The definition of a conjugate. Simply, conjugates are two complex numbers where one is a plus bi and the other one is a minus bi. And all the conjugate means is we multiply those two numbers, the i's will go away, we'll be left with a single real number. There are no imaginary parts. This is very, very useful to us because dividing complex numbers would be very difficult to do without conjugates. Let's take a look at the next visual. There's a division problem written as a fraction, 4 plus 3i divided by 2 minus 3i. And again, you could say, what is this all about? And I would say to you, this is interesting mathematics. Let's play with it a while and use it later on. Okay? And in fact, like I say, go major electrical engineering when you get to college, and you'll play with these complex numbers quite a bit. And the task, as indicated on the visual, is to make the denominator a real number. Why? Because if we have a complex number in the numerator, and the denominator is 6, all I need to do is to divide the real part of the numerator by 6, and then divide the coefficient of I, that's in the imaginary part, by 6, and I have a nice, easy-to-read, complex number. Well, how am I going to make that denominator real? We just saw that multiplying a complex number by its conjugate will make a complex number a real number. So let's look at the next visual, which shows us that we're going to take the 4 plus 3i over the 2 minus 3i and multiply top and bottom by 2 plus 3i. Why top and bottom? Why numerator and denominator? For those of you who like Latin words, because when we multiply a fraction by top and the bottom by the same number. In effect, we're multiplying by 1, and the fraction has the same value. It may look different, but it's equal. And so we multiply the numerator. 4 times 2 is 8. 4 times 3i is 12i. 3i times 2 is 6i. And 3i times 3i is negative 9. If you don't see that 3i times 3i is negative 9, rewind the tape and see about multiplying imaginary terms. We combine those like terms and we get negative 1 plus 18i. You'll notice in the denominator, we've simply said, hey, we know that the 2 times 3i and the negative 3i times 2 cancel, so all we got to worry about is 2 times 2, which is 4, and a negative 3i times a positive 3i, which is positive 9. On the bottom line, which is highlighted, we see our answer, negative 1 plus 18i all over 13. That's one way to write it. A second way, which looks more like our definition of a complex number, is indicated. We take and divide each of the parts by 13. Negative 1/13 plus 18/13 I. This is a complex number. It is the answer to the original division problem, 4 plus 3i divided by 2 minus 3i. We've divided a complex number by a complex number and gotten an answer that was a complex number. If that's what we want to do, and we've done it. There's something else we need to do, we need to learn about with complex numbers that come into play very later on. Those you will be taking trigonometry or senior math in high school, or perhaps in college taking college algebra, is dealing with the graphs of complex numbers. Now, you know, we actually graphed real numbers before, like when we were doing inequalities. We had a number line. And if x was greater than 6, we located 6 on the number line. And we said, that's 6. That's the graph of 6, is the point right there at the little tick mark that has 6 by it. We're going to graph complex numbers in the plane. And the next visual shows us exactly how to do that. We have our normal set of axes, the x and y, except the x-axis is marked real. That, the x-coordinate of a point, is the real value of the complex number. And the y-axis, you'll note, is marked imaginary, so that the y-coordinate of a point would be the coefficient of I for its imaginary part. Notice we have a point there. It's 4 over and 5 up. It's marked ordered pair 4, 5. And it says equals 4 plus 5i. The x-coordinate is the real part. The y-coordinate, the imaginary coefficient, 4 plus 5i. Also down on the negative part of the y-axis, you'll notice the point at negative 7. The ordered pair 0, negative 7, it says is equal to negative 7i. That's because we said a pure imaginary number, negative 7i, could be written as 0 minus 7i, and thus the point 0, negative 7. Where would the number 6 be? It would be the same as before, as we talked about. It would be on the horizontal axis, which is the real axis, 6 ticks over, and you'd have a mark, and it would be 6, or if you like, 6 plus 0i. Now, we started this lesson by talking about the use of the square root of negative numbers in the solution of quadratic equations. Let's go back to that and see how we can now get solutions with complex numbers. And so rather than saying no real solutions, we could say there's no real solution, but we can find the complex solutions to our quadratic equation. So let's take a look at the next visual, which has 1/2 x squared plus 3x plus 29 equals 0. Also, it's an opportunity to see that a, the lead coefficient, the coefficient of the quadratic term, can be a fraction. Okay. Remember the first thing we did, we wrote down A, B, and C. I haven't done that here because I'm trying to save space on the visuals. You should still be doing this. A is 1/2, B is 3, C is 29. B squared minus 4AC is 9, 3 squared, minus 4 times 1/2 times 29. Fortuitously, this is negative 49. Why do I say fortuitously? Because 49 is a square number, which means negative 49 is also a square number, but its square root is imaginary. And in fact, on the last line, we see that x is equal to negative 3, negative b, plus or minus the square root of negative 49, plus or minus 7i, all over 2a, which is 1. And of course, we never leave 1 in the denominator. We write the answer as negative 3 plus or minus 7i. What's the next thing we need to do? Hopefully, you're saying, I bet he wants us to check. And I do. And this is why we went through the arithmetic of complex numbers. Because checking one of these complex solutions can be a little tedious. You've got to be very careful because you're adding and subtracting and multiplying complex numbers. The one nice thing about it is that it's been determined that if you have a plus bi is a solution to your quadratic equation, then its conjugate, a minus bi, must be. So we need not check both answers. We only need to check negative 3 plus 7i. So let's take a look at the next visual, which looks a bit messy, and that's okay. And, you know, I'm going to go through this fairly quickly, but you might want to rewind the tape to this particular visual and just pause on your screen and look through it very carefully, and even turn the TV off and make sure that you can actually do this arithmetic. Because all I've done is taken the original equation, 1/2 x squared plus 3x plus 29 equals 0, and replaced the x with negative 3 plus 7i. Where x was squared, you'll notice on the first line I have negative 3 plus 7i times itself. I multiply, I combine like terms, and on the third line, which is highlighted, I get negative 20 minus 21i minus 9 plus 21i plus 29. What do I have? Equals 0. Everything cancels out. Is that good? Of course it is, because the original equation was that whole mess equals 0. I have proven that negative 3 plus 7i is an answer. If that's true, then negative 3 minus 7i is also an answer. Well, let's take a look at another problem. Next visual has another quadratic equation for us. X squared minus x plus 1 equals 0. Now, by the way, we know, because this lesson is entitled Imaginary Numbers, that this solution is going to include I. It's going to be a complex solution. Remember that on a test or a quiz, what you're going to have is these problems mixed up. And so don't always be looking for one type of solution or the other. If you follow my step-by-step procedure to solve a quadratic equation, I think you will not run into that problem. Okay, A is B is 1, B is negative 1, C is 1. B squared minus 4AC, 1 minus 4 equals 3. No, it doesn't. It equals negative 3. Be careful of those simple numbers. 1 minus 4, of course, is negative 3. Now, we have a negative, and of course 3 is not a square number, and that's why we did this problem, to see what happens if the discriminant is negative but not square. Well, we have the next line, x equals minus b, which is positive 1, plus or minus the square root of negative 3. And what we do is we take the I out. The square root of negative 1 is I, and what's left inside the square root is the 3. We can't take the square root of 3, so we leave it alone. And thus our answer, 1 plus or minus I, the square root of 3, all over 2. Now what are we going to do? We are going to check. Do we have to check both of them? Of course not. We just need to check 1 plus I, the square root of 3, over 2. By the way, if you wanted to write that as 1/2 plus or minus 1/2 I, the square root of 3, that's fine too. But generally, in these solutions, we leave the denominator across the entire complex numerator. All right, let's take a look at the next visual, which again looks a little busy, and that's because it is, because there's a lot of work involved. And rather than going step by step, all I'd want you to do is pause the tape, take a look at it. Make sure you understand what I've done. At a later time, see if you can do it by simply plugging in the 1 plus I, the square root of 3, all over 2 into the original equation. And you'll notice on the bottom line that whole thing equals 0, which is great. One thing I should mention, you may recall that the very first step in my procedure to solve a quadratic is to get the equation in ax squared plus bx plus c equals 0 form. The two equations we've done in this lesson are in that form. What if the equation was not in that form? You do the same thing, but when you check, remember to always check in the original equation, not in the equation in ax squared plus bx plus c form. We have one last thing I'd like to show you that I think is quite interesting. Look at the next visual. What we have here is a complex number, negative a half plus I, the square root of 3 over 2. A complex number with a fraction and a square root, kind of real messy, and it's cubed. Now, why am I doing that? Well, let me, humor me. Go along with me. I think you'll see why I'm doing this. There's a very good purpose involved here. Something that, again, will come into play in later mathematics courses where you're taking powers of complex numbers and learning, quote, easy ways to do it. On this particular visual, you'll see that I actually first squared. I took the complex number and multiplied it by itself. Again, it's a little messy, and I would suggest that you write this down, turn the tape off, multiply it, turn the tape back on in the pause mode, and make sure that you get the answer I got, which is negative a half minus I, the square root of 3 over 2. This is not the ultimate answer because that's simply that complex number squared. We want it cubed. In the next visual, we take the answer we just got, which was negative a half minus I, the square root of 3 over 2, and multiplied it by the original complex number minus a half plus I, the square root of 3 over 2. You say, wait a second, that kind of looks like a conjugate. And what happens, of course, is it is, and which means the imaginary parts drop out, and we wind up, strangely enough, with 1. That is, on the third line, it shows you, part that is shaded, shows you that the cube of negative a half plus I, the square root of 3 over 2, is 1. They say, big deal. I mean, it's kind of nice that you took this messy number and you multiplied it by itself and by itself again, and you got 1, but so what? What's the big deal? Why are you spending my time doing this? Because if you look at the next visual, you'll see that if you had the equation the cube root of 1 equals x, or x cubed minus 1 equals 0, they're both the same thing, you'll note. And I said, what was the solution? Before right now, you would have said, the only number I know that you can cube and subtract 1 to get 0, or the only number I know that's the cube root of 1 is 1. And you would have been right up to now. But now we know that negative a half plus I, the square root of 3 over 2, cubed is 1. And that means negative a half plus I, the square root of 3 over 2 is a cube root of 1. And now I ask you a very important question. What else is a cube root of 1? If you've been paying attention, remember we said that if you solve a quadratic and you get an answer that's complex, then its conjugate is also a solution. And therefore, as you'll see in the last visual, if you have the equation we had before, x cubed minus 1 equals 0, or x is the cube root of 1, there are 3 solutions. One of those solutions is 1, the number you already knew. Then negative a half plus I, the square root of 3 over 2. A complex number that you know, because I did it and hopefully you did it too, when you cube that complex number you get 1. And the third solution, minus a half minus I, the square root of 3 over 2, which also you could take the time if you want and cube it, you'll get 1, but you know it's true because it is the conjugate of the second solution. Which, of course, is interesting because now we know that the cube root, there are 3 of them, just like we knew there were 2 square roots for most numbers. And again, we can pursue this later on in this part of the trigonometry or college algebra course. So we've seen in this lesson that we have these imaginary numbers, which are written I, that we can allow that to stand for the square root of negative 1, which allows us to take the square root of a negative number. We can add, subtract, multiply, and divide these imaginary numbers, or in complex form with a real number plus or minus an imaginary part, a plus bi. We've used the conjugate to divide, so we can add, subtract, multiply, and divide complex numbers. We've looked at the graphs. We've looked at the complex solution to quadratic equations. And we've looked at the fact that when we take something as simple as the cube root of 1, we can actually get 3 answers, one of which is simple, and the other 2 are complex numbers. So we've covered some new material, and in fact, in the ensuing lessons, we're touching on some material you probably have not seen in Algebra 1. Okay, so you might want to review this tape to ensure you've got it. And in our next lesson, we're going to cover something called quadratic and rational inequalities. And I'm sure you can't wait to find out what they are. See you in Lesson 18.